This is an interesting one to end with. Set up the integral for the surface area of the ellipsoid. Pretty cool. So you see the equation of an ellipse right there. X squared over 25 plus y squared over 4 equals 1. We're going to revolve that about the x-axis and think about the surface area. So you imagine an ellipse, spinning. It's going to create kind of a football looking sort of a shape. If you think of a three-dimensional ellipse, we call an ellipsoid. And we'd like to know the surface area of this one. Okay. So we'll begin just by graphing that ellipse. Now, even things like, the equation of an ellipse, you can type that right in at Desmos. And it can graph things that are not functions. It's really sweet, and it'll give you that graph. Or maybe you remember how to do this. So you see my first couple drawings. Okay, so this ellipse, right, the center, the origin is the center, 0, 0. That number, 25, tells us to move horizontally 5 in both directions. And the 4 here tells us to move vertically 2 in both directions. And we connect all of that. We got our ellipse. And we're going to think of spinning this about the x-axis. Now, the truth is we're not actually going to spin the entire ellipse around the x-axis. We really only want to spin the upper half, the top half. That top half, if it spins all the way around, that creates the three-dimensional shape. We would not want to also spin the lower half because that would like double up on itself as it spun around. We want to spin a full 360 degrees, so we're only going to take that top part to create our shape. Okay. So I got my note there. We revolve only the top half. And now here's a way to make our work just a little bit faster, a little bit simpler. Because we've got this nice symmetry through the y-axis, only consider the first quadrant. If we only consider the first quadrant spinning around, well, then we can double our answer and we'll get the other side as well. Okay. And you can also see it's very tiny, but that's r of x. So again, you begin on your axis and then you go out perpendicular until you hit your curve. That is the radius at any given moment, any given x value. Okay, so we're going to find this surface area here around the x-axis and then multiply it by 2. Now keep in mind, we're only going to set up this integral. That's all they're asking us for. So how are we going to do this? Okay, in this case, they gave us the equation of that ellipse. So to get the equation here of the upper half, we need to solve for y. So that's the first thing we're going to do, and I just went right to it. Taking that equation of the ellipse, solving for y. So let's see if we can think through it. So subtracting the x squared over 25. Then you can multiply by 4 and then take a square root. Now when you take a square root of the 4, you're going to get a 2. So we just have the square root of the 1 minus x squared over 25. And we only need to consider the positive part, even though there would be a plus or minus, right? Only consider the positive because it's only the top half, the positive y values. Okay. So we will need, that's our function y, so we'll need a derivative. So here we go. I just left that constant multiple 2, and then the derivative here, the 1/2, 1 minus x squared over 25 to the negative 1/2. And then the derivative of the inside, think of that as negative 1 over 25 x squared, and your derivative is negative 2x over 25. Okay, and then simplifying, well, that 2 and that 1/2 canceling nicely. So let's say negative 2x over 25 from here, square root And it's very small in my writing there, but square root 1 minus x squared over 25. There's our simplified y prime. Okay. And we're kind of used to this pattern by now. We're going to square y prime squared. So the negative changes to a positive, and we've got 4x squared over 625. Parentheses, our square root gets taken away with the square 1 minus x squared over 25. Okay, and I like it just like this. You could distribute that 625. That would actually go very nicely. But I'm just going to leave it like that. We also need r of x. Let's go back to the drawing. In this case, since we're coming off the x-axis, r of x is simply the function, which we found right here in terms of y. So r of x, it's a vertical line, so that's a y, right? The length y. Well, that's what y equals. That's another way to think about it. Okay, and we're all set up now. So here we go, surface area. Remember, we were going to double this whole thing, so we want 2 times in front. 2 pi integral. We are going from 0 to 5. So 0 to 5, and then we've got r square root 1 plus y prime squared right there, dx. There's the setup for this surface area. We've got it. Now, a couple of comments. Maybe you prefer not to double. You actually don't have to. It's really not a big deal if you're not actually going to go about doing the integral and plugging the numbers in. You don't have to double here. You could say the integral is from -5 to +5. -5 to +5, and then you would not have to double. Although I would recommend, if you were actually going to go through with this integral, make it from 0 to 5 and then just stick it ×2 in front. It makes it much easier when you plug in your numbers later. Let's also just talk for a moment about what if we did want to go further. And hey, if you guys want to do that on your own, I certainly encourage you to. This looks horrible at first, right? But it's actually not nearly as bad as what you think. So, of course, we could just pull this 2 right on out and get 8 pi out here. Then we've got a square root times another square root. We could put that all under one big square root and distribute the 1 minus x squared over 25. And you notice it would cancel out with this one. And we could start to clean it up and see what happens from there. So if you want to explore that on your own, I certainly welcome you to do that. Although here, we're just setting up the integral. So we're done at this point. Okay, well, hey, that is it for surface areas of revolution. Go check out the homework. Good luck.